Welcome to Sri Learning Academy. Let's simplify message queues. Message queues are one of those operating system concepts that sound complex at first, but once you connect them to real life communication, they start to feel very natural. To understand message queues properly, it helps to remember what we already discussed earlier about interprocess communication. We learned that processes often need to talk to each other. They may be part of the same application, or they may be completely different programs working together. Since processes run in separate memory spaces, they cannot simply read or write each other's data. The operating system has to provide safe and controlled ways for this communication to happen. One such way is message passing, and message queues are a very important part of that idea. Think about how people communicate when they are not in the same room. One option is a phone call, where both people must be present at the same time. Another option is leaving a voicemail or a message in an inbox. The sender leaves a message and goes away. The receiver can come later, check the inbox, and read the message when ready. Message queues work very much like that inbox model inside an operating system. In simple terms, a message queue is a data structure maintained by the operating system that stores messages sent by processes. One process sends a message to the queue, and another process receives a message from the queue. The key point here is that the sender and receiver do not need to interact at the same time. This makes message queues very useful in systems where processes run at different speeds or have different priorities. Let us take a simple example to make this clear. Imagine a printing system in an office. Many employees send print requests from their computers. Each request is a job that needs to be printed. The printer itself can only print one job at a time. So, what happens to the other requests? They are placed in a print queue. Each computer sends its print request to the queue and does not wait for the actual printing to finish. The printer takes jobs from the queue one by one and prints them. In this example, the print queue behaves very much like a message queue. The computers are the sender processes, the printer service is the receiver process, and the print jobs are the messages. Inside an operating system, message queues work in a similar way. A message usually has two parts. One part is the actual data, which could be text, numbers, or structured information. The other part is metadata, such as the message type or priority. The operating system stores these messages in the queue in an organized manner, usually following rules like first come, first served, or priority based ordering. One important feature of message queues is that they are kernel managed. This means the operating system controls the queue, not the user programs directly. Processes interact with message queues using system calls. A process can request the OS to create a message queue, send a message to it, or receive a message from it. Because the OS is in control, it can enforce security and synchronization rules. This prevents one process from corrupting data meant for another process. Now, let us look at how message queues differ from pipes, which we discussed earlier. Pipes also allow processes to communicate, but pipes are usually unidirectional and work best for simple, continuous streams of data. Message queues, on the other hand, allow discrete messages. Each message is separate and clearly defined. With message queues, you can also assign priorities to messages, which is not something basic pipes support easily. This makes message queues more flexible for complex communication patterns. Consider a real world analogy from customer service. Imagine a help desk system. Customers submit tickets describing their problems. Some tickets are marked as urgent, while others are normal. The support team picks tickets based on priority. This is exactly how priority based message queues work. A process can send an urgent message, and the receiving process can choose to handle urgent messages before normal ones. Another big advantage of message queues is synchronization. Earlier, we saw that synchronization is a major concern when multiple processes are involved. Message queues help with this naturally. If a process tries to receive a message and the queue is empty, the operating system can block that process until message arrives. The process does not waste CPU time by repeatedly checking the queue. Similarly, if the queue is full, the OS can block the sending process until there is space. This control blocking helps the system run efficiently. Let us take an example from a producer-consumer scenario. Imagine a sensor application where one process collects temperature readings and another process analyzes them. The sensor process produces data at regular intervals. The analysis process may take longer to process each reading. A message queue fits perfectly here. The producer sends each temperature reading as a message to the queue. The consumer reads messages at its own pace. If the consumer is slow, messages wait safely in the queue. If the consumer is fast, it simply reads messages as soon as they arrive. Message queues also help with decoupling processes. This means processes do not need to know details about each other. The sender only knows the queue, not who exactly will read the message. The receiver only knows it will get messages from the queue, not who sent them. This design makes systems easier to modify and extend. For example, you could add another process that also reads messages from the same queue for logging purposes without changing the sender process at all. In Unix and Linux systems, message queues come in different forms. Traditional system V message queues allow messages to be tagged with types, so a process can choose to receive only messages of a certain type. POSIX message queues provide a slightly different interface and are often easier to use in modern applications. While the underlying APIs differ, the core idea remains the same. The OS manages a queue of messages and processes communicate through it safely. There are also some limitations to message queues. Since messages are stored in kernel space, there are limits on how many messages can be stored and how large each message can be. If these limits are not managed properly, a queue can fill up and block senders. Message queues are also generally slower than shared memory because data has to be copied from one process to the kernel and then to another process. This is why in performance critical systems, shared memory is often preferred, with additional synchronization mechanisms. We will explore that in the next topic. Despite these limitations, message queues are widely used because of their simplicity and reliability. They are especially useful in systems where safety, clarity, and structured communication are more important than raw speed. Many server applications, background services, and real time systems rely on message queues to coordinate work between different components. To sum it up, message queues provide a mailbox like communication system inside the operating system. Processes send messages without worrying about when they will be received. The operating system ensures messages are stored, ordered, and delivered correctly. By doing this, message queues solve two big problems at once. They allow processes to communicate and they help synchronize their actions. As we move forward to shared memory and signals, keep this idea in mind. Each IPC mechanism exists because different situations need different communication styles, and message queues are one of the most practical and human friendly solutions among them. That is it for this video. See you in the next one.